So our project is based on reinforcement learning. In reinforcement learning, an agent interacts with the environment and gains the rewards. Accordingly, it learns the policy. So these are the table of contents. Here in our project, we introduced a algorithm called MA-MPSAC. MP means meta policy. SAC is soft Actor-Critic. MA stands for multi-agent. So our project deals with multiple agents, not a single agent. So in our project, in this algorithm, we have introduced a better experience replay buffer. Its architecture is entirely different from the traditional experience replays, and our algorithm is stable, and we normalize the inputs so that they fall within a range, and it doesn't face a problem like exploding gradients. For more exploration, we have introduced a noise to the actions. Multiple agent learning can be done in can learn two strategies. One is cooperative and the other one is competitive. In cooperative, multiple agents cooperate to achieve a common goal, but in competitive it is the reverse. One agent tries to achieve a goal, the other agents will compete with the first agent. Agents can be homogeneous in multiple agent setup. Homogeneous mean in the sense all the agents will have same action space. They cannot perform different actions. All will perform same actions. In heterogeneous multiple agents, each agent will be having different skill set, different action space. Here our project objectives goes like this. Blue agents should capture all red in combat. In keep away, green should reach green. In physical deception, these two good agents should reach the target, and and this adversary will try to stop good agents reaching the target. In predator prey, all these three red agents called predators should reach this green dot, which is called prey. Our project can be used in a soccer setup where multiple soccer agents are coordinating with each other to perform goal. Then the other agents are acting as a competitive agents. Here in figure B, we can see robotic servers where these robots will interact with each other, so that no two robots serve the same table. In example C, we are showing a self-driving car. All the self-driving cars in a crossroad situation communicate with each other and cross the road so that both no two cars collide each other. Literature survey, here we have listed out five we have listed out 5 algorithms, and this is our proposed algorithm. So in these 5 algorithms, we can see that most of them doesn't support multi-agent setup, and the architecture here is also different. In our case, we use 2 actors and 3 critics, but most of the algorithms use 1 actor and 1 critic. Our algorithm is stable. We have normalized the inputs as well. So one more problem we face in the traditional algorithms is exploitation. Instead of exploration, sometimes it happens that agents will go on exploiting it and doesn't learn anything. It doesn't learn proper abstractions. So it does. In existing system, we have listed out all these in the previous shown algorithms. In the proposed algorithm, we have made experience replay buffer are centralized, updates are soft updates, the policy is a meta policy, and the architecture is mostly decentralized. We have 5 modules in total: training, agents, networks, experience, results in training. Multiple threads are being rolled out. These threads will handle different areas. By default, this thread count is 1. Agents, in agents, if the input is, suppose you are an agent in a game, then what you can have, what the input you have is the action space, the observation space. The what the agent should perform is an action. So the input to agent is observation space, output is action. We have defined networks. How the agent will perform an action is based on the networks. The networks are actor and critic. We have defined it in another module called networks. It's here the actual layers have been defined, like dense layers and all. Experience module shows the uh, previous experience. Results will show the plots and performance of agents. And this is a design of our project. Here, all these 3 things are the agents. The detailed architecture of agents is here. It has 3 actor networks and 2 critic networks. The input to actor networks is observation state, and output is action. So the same for all three actor networks. So there will be 3 action outputs. But an agent can perform only 1 action at a time. So there is an ensemble going here, which takes all the 3 actions and performs a mean of the actions, and that action will be performed by the agent. Once the action is performed by the agent, the observation state goes to O dash. So the input is O. The input is O. The action is A. The next state is O dash, and we'll also get a reward after performing an action. So all these things, so all these agents will generate all these 4 things: O dash, R, and A. All those things will be stored in experience replay, as shown here: O, A, O dash, and R for agent across the time. So we'll take we doesn't need the full experience replay always. So we take mini batch of it, a random sample. So we took this random sample uh, in this example. So this is a mini batch. After this, a critic is someone who corrects the actors. They will tell the actors their defaults and all. So a critic is used to calculate the actor loss here, just like in the case of movies. Uh, so the so gradient calculation, loss calculation, and update function. All these things happen within the critic, and sends the feedback to the agents. Then at the final step is updating the target networks by parameter sharing. What are target networks? Target networks are exact clones of the actor networks, but a time delayed clones. Uh, Say this is at time step 10, time step 1. The target, say the actual network is at time step 10. The target network timestamp will be 1 or 2. It is delayed by some time. So all these since they are exact clones, the weights of this network will be equal to the weights of this network. but we are performing soft updates instead of the entire copy, which means a factor of tau weights will be copied to the targets. This is about the architecture. And till now we are talking about actor and critic network, which are three dense layers and one softmax layers with relay activations in our in our setup, where input is observation space and output is action, as told before. In actor, the critic network input is next state, action, and reward. The output is actor loss. These are hardware requirements and software requirements. In algorithm, we can see that there's a meta policy. Um, there's an experience replay after performing an execute action for each agent to observe reward and a new state. And we're storing it in experience replay. We are taking mini batch of experience replay and updating actor and critic networks. And finally, after performing for everything, we are updating our target network. Then we have tested with a few problems, like blue blocks should capture all red blocks, and it passed well. Like predators must capture all prey, it passed well. Here in the results, we'll show it by executing. Observation, will talk about observation after showing the execution. We conclude saying that we have introduced a proper centralized experience replay and and meta policy. Our algorithm is stable. It doesn't need any supervision because we are not collecting any data or labeling any data. So it will learn by itself. The updates are soft updates and for target networks. The only drawback in our algorithm is architecture is complex and experience replay is also complex. Since we are traditionally it is only only two networks, actor and critic, but now we have two actors and three critics, so it is five networks in our algorithm. So that is an overhead, we can say. Future work, obviously there are a lot of openings to the real world, to solve real world problems by our suggested algorithm. One of them is soccer, as we have seen. The other is in construction sites, and the other one, which we already told, is integrated chips and etc. Uh, im- uh, and implementation wise, there is something called imitation learning, uh, where a person actually performs actions. Uh, Person performs actions which will be imitated by the agent. Then it is left to uh, learn by reinforcing, learn by guessing and all.